Section 1 Introduction. We aim to enhance the capabilities of large language models, LLMs, to interact effectively with various tools, such as APIs, to perform complex tasks. By merging LLMs with APIs, we can significantly increase their usefulness, enabling them to act as efficient intermediaries between users in a wide range of applications. While open-source LLMs like LLaMA and Vicuña have shown versatility through instruction tuning, they still struggle with more complex tasks, such as understanding human instructions and interacting appropriately with APIs. This is because current instruction tuning mainly focuses on basic language tasks, rather than tool use. On the other hand, state-of-the-art LLMs like ChatGPT and GPT-4, which have shown impressive abilities in using tools, are closed source, making their inner workings unclear. This restricts the democratization of AI technologies and limits community-driven innovation and development. We believe it's crucial to enhance open-source LLMs to master diverse APIs skillfully. Previous attempts to build instruction tuning data for tool use have not fully unlocked the tool use capabilities within LLMs and have inherent limitations. These include a limited range of APIs, a constrained scenario that only involves one tool, and inferior planning and reasoning. To address these issues, we introduced ToolLLM, a comprehensive tool use framework for data construction, model training, and evaluation. We first collect a high-quality instruction tuning dataset called ToolBench, constructed using the latest ChatGPT. The creation of ToolBench involves 3 stages: API collection, instruction generation, and solution path annotation. We gather over 16,000 APIs from Rapid API, spanning 49 diverse categories. We then use ChatGPT to generate diverse instructions for these APIs, covering both single-tool and multi-tool scenarios. Finally, we annotate high-quality responses to these instructions. To improve the planning and reasoning ability of LLMs, we develop a novel depth-first search-based decision tree, DFSDT. This allows LLMs to evaluate multiple reasoning paths and make deliberate decisions. To evaluate the tool use capabilities of LLMs, we develop an automatic evaluator, ToolEval, backed up by ChatGPT. It measures the ability to successfully execute an instruction within limited budgets, pass rate, and compares the quality and usefulness of 2 solution paths, win rate. By fine-tuning LLaMA on ToolBench, we create ToolLLaMA. Our evaluation shows that ToolLLaMA can handle both single-tool and complex multi-tool instructions. It can also adapt to new APIs effectively, requiring only the API documentation. We also show that our DFSDT enhances the reasoning capabilities of LLMs and achieves significantly better performance than React. Additionally, we train a neural API retriever that recommends relevant APIs for each instruction, alleviating the need for manual selection from the large API pool. In conclusion, our work aims to empower open-source LLMs to execute complex instructions involving diverse APIs in practical scenarios. We hope this will inspire further research in the intersection of instruction tuning and tool use. Section Summary. Tool learning aims to enhance the capabilities of open-source language models, LLMs, by integrating them with APIs, enabling them to effectively interact with various tools and accomplish complex tasks. However, current open-source LLMs lack the sophistication in understanding human instructions and interacting with tools, while closed-source LLMs with impressive tool use competencies limit the democratization of AI technologies. To address these limitations, the authors introduce ToolLLM, a framework that constructs a high-quality instruction tuning dataset, enhances model reasoning with a depth-first search-based decision tree, and develops an automatic evaluator. The results demonstrate ToolM's compelling capability to handle both single-tool and complex multi-tool instructions, as well as its robust generalization to previously unseen APIs. Section 2 Dataset Construction. In this section, we'll explain how we built ToolBench, a process that involved 3 steps: collecting APIs, generating instructions, and annotating solution paths. We used ChatGPT, GPT 3.5 Turbo -16K, to complete this process, which required minimal human intervention and can be easily adapted to include new APIs. Let's start with how we collected APIs. We used Rapid API, a popular API marketplace that helps developers find and use thousands of real-world APIs, making it easier to incorporate various services and data sources into their applications. Developers only need a Rapid API key to access and test a wide range of APIs. Rapid API organizes APIs into 49 broad categories, like sports, finance, and weather, to help developers find the most relevant APIs for their needs. It also offers more specific groupings, known as collections, which include Chinese APIs, top AI-based APIs, and database APIs. APIs within the same collection usually share similar features or objectives. Each tool in Rapid API can consist of multiple APIs. For each tool, we collected the following information: the tool's name and description, the host's URL, and all the APIs associated with the tool. For each API, we noted its name, description, HTTP method, required and optional parameters, request body, executable code snippets for API calls, and an example API call response. This comprehensive metadata is a valuable resource for language models, LLMs, to understand and use the APIs effectively, even without prior knowledge. Initially, we collected 10,853 tools, 53,190 APIs, from Rapid API. However, the quality and reliability of these APIs can vary greatly. Some APIs might not be well maintained and could return errors like 404. To ensure that ToolBench only includes reliable and functional tools, we implemented a strict filtering process. First, we tested each API to see if it was working. Any APIs that failed this basic test were discarded. Next, we made API calls to get an example response, which we evaluated based on response time and quality. We removed any APIs that consistently had long response times or provided low-quality responses, such as HTML source codes or other error messages. After this rigorous filtering process, we were left with 3,451 high-quality tools, 16,464 APIs. Section Summary. In this section, we describe the construction process of ToolBench, which involves 3 stages: API collection, instruction generation, and solution path annotation. We utilize ChatGPT to complete the entire procedure with minimal human supervision, making it easily extendable to new APIs. We start by introducing Rapid API, a marketplace that connects developers with various APIs, and then crawl and filter APIs to ensure the reliability and functionality of the final toolset. Section: API response compression. We've noticed that the responses we get from APIs can sometimes contain unnecessary information and be too lengthy to process with language learning models, LLMs. This is a problem because LLMs have a limit to the amount of context they can handle. To solve this, we've developed a method to compress these responses, reducing their length while keeping the important information intact. We use ChatGPT to analyze a sample response from each API. Since each API has a standard response format, we can identify and remove less important parts of the response to make it shorter. To help ChatGPT understand the API's function, we provide it with the API's documentation, which includes the tool's name, description, API description, parameters, and an example API response. We also give ChatGPT 3 examples of original API responses and their compressed versions, written by experts. This way, we can develop a compression strategy for all APIs. If an API response is longer than 2048 tokens, we compress it by removing less important information. If it's still longer than 2048 tokens after compression, we only keep the first 2048 tokens. Creating high-quality instructions is a 2-part process. We need diversity to ensure that the LLMs can handle a wide range of API usage scenarios, which makes them more versatile and robust. We also need to consider multi-tool usage, as real-world situations often require the use of multiple tools. This improves the practicality and flexibility of LLMs. To generate instructions, we use a bottom-up approach. Instead of coming up with instructions first and then looking for relevant APIs, we start with the APIs we have and create various instructions that involve them. We define the total set of APIs as S_API. At each step, we select a few APIs from this set, which we call S_N_sub. We then use ChatGPT to understand the functions of these APIs and how they interact. From this, we generate possible instructions that involve the APIs in S_N_sub and identify relevant APIs for each instruction. We use different strategies to sample APIs, ensuring that we cover all APIs and most of their combinations. This ensures that our instructions are diverse. The prompt for ChatGPT includes a general description of the task, comprehensive documentation for each API in S_N_sub, and 3 examples of ideal instruction generation written by human experts. In total, we wrote 12 examples for the single tool setting and 36 for the multi-tool setting. We randomly select 3 examples at each step. The overall generation process can be summarized as follows. ChatGPT generates instructions and relevant APIs based on the APIs in S_API, and the examples in S_seed. Section summary. When analyzing API responses, we found that some are too long and contain redundant information, which poses a problem for LLMs with limited context length. To address this, we compress the responses by removing unimportant keys using ChatGPT. For instruction generation, we adopt a bottom-up approach by starting with collected APIs and crafting instructions involving them, ensuring diversity and multi-tool usage. We use prompts that include API documentation, in-context examples, and seed examples written by experts to train the model. Section. Sampling strategies for different scenarios. We're going to discuss the different strategies we use for creating instructions in various scenarios. As illustrated in the figure, when we're dealing with single tool instructions, which we'll call I1, we go through each tool one by one and create instructions for their APIs. However, when we're dealing with multiple tools, things get a bit more complicated. Because the connections between different tools in Rapid API are few and far between, if we were to randomly select tool combinations from the entire set, we'd often end up with a bunch of unrelated tools that can't be covered by a single instruction in a natural way. To get around this problem, we use the hierarchy information from Rapid API. We know that tools that belong to the same category or collection usually have similar functions and goals. So, we randomly pick 2 to 5 tools from the same category or collection and sample up to 3 APIs from each tool to create the instructions. We call the instructions we create this way intra-category multi-tool instructions, or I2, and intra-collection multi-tool instructions, or I3, respectively. We've found through thorough human evaluation that these instructions are quite diverse and cover a wide range of practical scenarios. We also use Atlas V to create visualizations for these instructions to back up our claim. Once we've created the initial set of instructions, we filter out those with relevant APIs that don't actually exist in the subset of text N. In the end, we've collected over 200,000 pairs of instructions and relevant APIs that meet our criteria, including 87,413 pairs for I1, 84,815 pairs for I2, and 25,251 pairs for I3. Now, let's talk about how we annotate the solution path. As shown in the figure, given an instruction, which we'll call inst**, we ask ChatGPT to search for a valid sequence of actions, A1, A2, and we treat this multi-step decision-making process as a multi-round conversation for ChatGPT. At each step, the model generates an action, based on previous interactions. For each action, we ask ChatGPT to specify which API to use, the specific parameters for an API call, and its thought. So, an action has the following format: thought, API name, parameters. The decision space is the combination of the thought, available APIs, and possible parameters, which is essentially infinite. To make use of the function call feature of GPT 3.5 Turbo-16K, we treat each API as a special function and feed its API documentation into the ChatGPT's function field. This helps the model understand how to call the API. For each instruction, inst**, we feed all the sampled APIs, subset of N, to ChatGPT's as available functions instead of only its relevant APIs, rel. This gives the model access to a wider range of APIs and expands the action space. To finish an action sequence, we define 2 additional functions, namely, finish with final answer, and finish by giving up. The first function has a parameter that corresponds to a detailed final answer to the original instruction. The second function doesn't have any parameters and is used when the provided APIs can't successfully complete the original instruction after multiple rounds of API call attempts. Section summary. For single tool instructions, we generate instructions for each tool's APIs. However, in the multi-tool setting, randomly sampling tool combinations often leads to irrelevant tools. To address this, we randomly select 2 to 5 tools from the same category, collection, and sample APIs to generate instructions. We evaluate the instructions and provide visualization using Atlas V. In the solution path annotation, we prompt ChatGPT to search for a valid action sequence based on previous interactions. We treat each API as a special function and feed its documentation to ChatGPT. We also define functions to finish an action sequence with a final answer or by giving up when APIs cannot complete the instruction. Section. Depth-first search-based decision tree. In our initial studies, we've noticed that traditional methods like COT or React have certain drawbacks when it comes to decision-making. Firstly, there's the issue of error propagation, where one wrong move can lead to a chain of mistakes, trapping the model in a faulty loop. This could manifest as repeatedly calling an API incorrectly or imagining APIs that don't exist. Secondly, these methods tend to explore only one possible direction, despite the action space being infinite. This limited exploration means that even advanced models like GPT-4 often struggle to find a valid solution path, making annotation a challenge. To address these issues, we suggest building a decision tree to broaden the search space and increase the chances of finding a valid path. As shown in the figure, our depth-first search-based decision tree, DFSDT, allows the model to evaluate different reasoning paths and decide whether to continue along a promising path or abandon a current node. For instance, if an API call fails at a certain node, the model can choose to give up on that node and expand a new one. When expanding nodes, we aim to diversify the child nodes and broaden the search space. We do this by prompting ChatGPT with information from previously generated nodes and explicitly encouraging the model to create a unique node. We opt for a depth-first search, DFS, over a breadth-first search, BFS, because we only need to find one valid path to complete the annotation. Using BFS would result in too many OpenAI API calls before reaching a terminal node, which could either be a finish with final answer node or a finish by giving up node. In practice, it's crucial to strike a balance between effectiveness and costs, with the latter being the number of OpenAI API calls. As such, we choose to perform a pre-order traversal, a type of DFS, for our DFSDT. This approach achieves similar performance to DFS but at a significantly reduced cost. In the end, we generate 12,657 pairs of instructions and solutions, which we use to train ToolLLaMA. While it's possible to create more training instances, we find that these 12,657 instances already provide satisfactory generalization performance. Section summary. The conventional methods of decision-making, such as COT or REACT, have limitations like error propagation and limited exploration, which make it difficult for models like GPT-4 to find valid solution paths. To address this, we propose a depth-first search-based decision tree, DFSDT, that expands the search space and increases the chances of finding a valid path. By using DFS instead of BFS, we can finish the annotation as soon as one valid path is found, reducing costs while maintaining effectiveness. This approach generates 12,657 instruction solution pairs, which are used to train ToolLLaMA and achieve satisfying generalization performance. Section 3 Experiments. In this section, we'll be discussing the experiments we conducted to assess the performance of our tool, ToolLLaMA. We'll first explain the evaluation metric we used for ToolLLaMA, then we'll discuss how we evaluated the effectiveness of the API retriever and DFSDT. Finally, we'll present the experiments and their results. We developed an evaluation tool called ToolEval, which is based on the Alpaca eval model. This tool was necessary because it's not practical to have a fixed solution path for each test instruction due to the changing nature of APIs. It's also important that all models use the same version of APIs during evaluation. Since human evaluation can be time-consuming, we opted for an efficient machine evaluator. ToolEval uses two evaluation metrics. The first is the pass rate, which measures the percentage of instructions that were successfully completed within a set number of actions, 200 in our case. This metric assesses the ability of a language learning model, LLM, to execute instructions, which is a fundamental requirement for effective tool use. We consider an instruction to be successfully completed if the final action is finish with final answer. We also have rules in place to check the content of each final answer and exclude any false positives. The second metric is the win rate, which measures the quality of the completed instruction, not just whether it was completed. This is done by comparing two solution paths for a given instruction. We have a set of criteria that define a better path, and these criteria are used as prompts for the ChatGPT evaluator. We present the instruction and two solution paths to the evaluator, who then indicates a preference. We repeat this process multiple times to improve reliability, and then calculate the percentage of times each solution path was preferred. To ensure the reliability of the ChatGPT evaluator, we tested it with three different methods: ChatGPT plus React, GPT-4 plus React, and ChatGPT plus DFSDT, on 600 test instructions. We then had humans annotate their preferences for these solutions. Our ChatGPT evaluator showed a high correlation of 75.8% with human annotators, indicating that it produces evaluation results very similar to those of humans. We also found that our automatic evaluator was more consistent than human annotators, with a lower variance in scores. Section summary. In this section, we conduct experiments to evaluate the performance of ToolLLaMA. We introduce the evaluation metric for ToolLLaMA, which includes the pass rate and win rate. The pass rate measures the proportion of successfully completing an instruction, while the win rate compares different solution paths for a given instruction and determines the preferred path. We validate the reliability of our ChatGPT evaluator by comparing its results with human annotators and find a high correlation of 75.8%. Section 3.2 Preliminary Experiments. In this section, we'll discuss our initial experiments, focusing on the API retriever and comparing DFSDT and React. Our API retriever is designed to find APIs that are relevant to a given instruction. We used the sentence BERT training method to create a dense retriever based on BERT base. This model turns the instruction and API document into two separate embeddings, and their similarity determines their relevance. During training, we treated the APIs relevant to each instruction as positive examples and also selected a few APIs as negative examples for contrastive learning. We compared our model to the BM25 and OpenAI's text embedding ADA002, API7, using NDCG to measure retrieval performance. We trained and evaluated our model on single tool instructions, I1, intra-category multi-tool instructions, I2, and intra-collection multi-tool instructions, I3. We also combined all the instructions and conducted training and evaluation. As the results in the table show, our API retriever consistently outperformed BM25 and ADA embedding across different types of instructions. The high NDCG score shows its effectiveness in API retrieval. Moreover, the NDCG score of I1 was much higher than I2 and I3, indicating that single-tool instructions are easier for API retrieval than multi-tool instructions. Next, we compared DFSDT and React before the solution path annotation. Using ChatGPT, we compared DFSDT and React for three types of instructions, with 1,000 examples for each. We used the pass rate for evaluation. Since DFSDT uses more OpenAI API calls than React, we created a React at N baseline for a fair comparison. This baseline performs React multiple times until the total costs match those of DFSDT. If React at N finds a valid solution, we consider it a pass. The results in the table show that DFSDT significantly outperforms the two baselines in all scenarios, indicating that DFSDT is a more cost-effective method for solution path annotation. We also found that DFSDT's performance improvement is more noticeable for more difficult instructions, i.e., I2 and I3, than for simpler instructions, I1. This suggests that DFSDT can solve complex instructions that the basic React cannot, regardless of how many times it is performed. Including such hard examples in our dataset can fully demonstrate the tool use capabilities for complex scenarios. Section summary. The API retriever is a model trained using sentence BERT to retrieve relevant APIs based on the similarity of instruction and API document embeddings. It outperforms baselines in API retrieval, with higher NDCG scores indicating its efficacy. DFSDT is shown to be superior to React in terms of pass rate and cost efficiency for solution path annotation, especially for harder, more complex instructions. Section ToolLLaMA. We've made some adjustments to the LLaMA 7b model to create our own version, which we call ToolLLaMA. We've trained this model using pairs of instructions and solutions. The original LLaMA model was designed to handle sequences of up to 2048 units in length, but we found that this wasn't sufficient for our needs, as the responses generated by our tool can be quite lengthy. To overcome this, we've used a technique called positional interpolation to increase the maximum sequence length to 8,192 units. We've trained our model to handle multi-round conversations, and we've kept the format of the training data the same as that used by ChatGPT. However, since it's not clear how ChatGPT handles the function call field, we've simply added this information to the input as part of the prompt for ToolLLaMA. Our hope is that by increasing both the number and diversity of instructions and unique tools in our training data, ToolLLaMA will be able to handle new instructions and APIs that it hasn't seen during training. This is important because users can define their own APIs and expect ToolLLaMA to adapt based on the documentation. We've tested ToolLLaMA's ability to generalize in three ways. 1. By giving it unseen instructions for the same set of tools used in the training data. 2. By giving it unseen tools that belong to the same category as the tools used in the training data. And 3. By giving it unseen tools that belong to a different category than the tools used in the training data. We've conducted experiments in three scenarios: single-tool instructions, multi-tool instructions within the same category, and multi-tool instructions across different categories. For the first two scenarios, we randomly selected 6 categories for testing, leaving the remaining 43 categories for training. For the first scenario, we evaluated all 3 levels of generalization. For the second scenario, since the training instructions already involve different tools of the same category, we only evaluated levels 1 and 3. For the third scenario, we only evaluated level 1, as it already covers instructions that involve various combinations of tools from different categories. For each test instruction, we provided the model with the correct APIs, simulating a situation where the user specifies the API set they prefer. Section Summary. The ToolLLaMA model is fine-tuned using instruction solution pairs and extends the context length to 8192 using positional interpolation. It aims to evaluate its generalization ability at 3 levels: unseen instructions for the same set of tools, unseen tools in the same category, and unseen tools in a different category. The evaluation is performed on 3 scenarios: single-tool instructions, intra-category multi-tool instructions, and intra-collection multi-tool instructions. Section: Baselines. We're going to discuss the baseline models and main results of our study. Initially, we couldn't use the original LLaMA model directly for our tasks because it wasn't fine-tuned for them. So, we opted for 2 versions of LLaMA, namely Vicuña and Alpaca, which were fine-tuned for general-purpose instruction tuning on dialogue data. Both of these models have proven to be effective at following instructions. We worked on enhancing their abilities to use tools by carefully crafting prompts for them. For comparison, we also used the teacher model, ChatGPT, and OpenAI text DaVinci 003 as our baseline models. We applied a method called DFSDT to all these models and another method called React to ChatGPT. When we calculated the win rate, we compared each model with ChatGPT React. Now, let's talk about the main results. We found that our model, ToolLLaMA, performs significantly better than the conventional method for tool use, ChatGPT React, in both pass rate and win rate. This shows that ToolLLaMA has superior generalization abilities. Moreover, ToolLLaMA also outperformed text DaVinci 003 when combined with DFSDT. Despite our extensive efforts to improve Vicuña and Alpaca through prompt engineering, neither of them could follow any instructions in the tool use scenarios. This highlights the limitations of current instruction tuning methods, which are primarily focused on improving language skills. In general, ToolLLaMA showed competitive performance in all scenarios. Its pass rate was slightly lower than that of ChatGPT combined with DFSDT. However, in terms of win rate, ToolLLaMA was on par with, and even surpassed, ChatGPT combined with DFSDT in the I2 CAT setting. These results show that our ToolBench can effectively bring out the tool use capabilities of language models and enable them to skillfully handle even unseen APIs for various instructions. We also integrated our API retriever with ToolLLaMA. In real-world situations, users might not be able to manually suggest APIs from a large pool. To simulate this, we replaced the ground truth APIs with the top 5 APIs recommended by our API retriever. The results showed that using our API retriever only slightly reduced the pass rate compared to the ground truth API set. The average win rate of ToolLLaMA was 49.8, which is quite impressive considering the large pool, over 16,000, of APIs from which our API retriever selects. This provides strong evidence of our API retriever's excellent ability to find relevant APIs. Interestingly, we noticed a slight increase in the win rate in several scenarios when using the API retriever. This suggests that the ground truth API set contains many APIs that could be replaced by ones with better functionalities, which our API retriever successfully identified. Section Summary. The authors compared different models for tool use, including LLaMA variants, Vicuña and Alpaca, ChatGPT, and OpenAI text DaVinci 003. They find that ToolLLaMA outperforms ChatGPT React in pass rate and win rate, demonstrating superior generalization abilities. However, Vicuña and Alpaca fail to pass any instructions, highlighting the limitations of current instruction tuning methods. Additionally, integrating an API retriever slightly diminishes the pass rate but improves the win rate, indicating the retriever's ability to identify relevant APIs. Section: Comparing DFSDT with React. We're comparing DFSDT with React here. Think of React as a simpler version of DFSDT. Even though we trained our model, ToolLLaMA, using data generated by DFSDT, it can work with either React or DFSDT when making decisions. We've compared these two decision-making strategies directly and the results are in the table. DFSDT comes out on top, with a significantly higher success rate in all scenarios. This highlights DFSDT's superiority over React, showing that it performs better in decision-making tasks. Moreover, when we compare these results with those in the table, it's clear that DFSDT's improvements over React are more noticeable for ToolLLaMA than for ChatGPT. This suggests that expanding the decision-making options is crucial for models with weaker reasoning abilities. This insight could be useful when applying DFSDT to smaller models in real-world situations. We've also been working on making ToolLLaMA more efficient in terms of parameters. In our earlier experiments, we fine-tuned all of LLaMA's parameters to create ToolLLaMA. To make it more efficient, we used a well-known method called LoRa that's known for its parameter efficiency. However, the table shows that while we did improve parameter efficiency, it came at the cost of performance. We're hopeful that future methods will be able to improve efficiency without compromising performance. Recent research has highlighted the growing ability of language learning models, LLMs, to master tools and make decisions in complex environments. When these models can access external tools, they gain real-time factual knowledge, multimodal functions, and specialized skills in specific areas. However, open-source LLMs are still not as good at using tools as state-of-the-art, SOTA, LLMs, and it's not clear how SOTA LLMs acquire their tool-using abilities. In this paper, we're trying to close this gap and understand the underlying mechanisms. Section Summary. The paper compares the decision-making strategies of DFSDT and React in the ToolLLaMA model, showing that DFSDT achieves a higher pass rate and is preferred across all scenarios, highlighting its superiority over React. Additionally, the study finds that DFSDT brings more significant improvements to ToolLLaMA than ChatGPT, emphasizing the importance of expanding the search space for models with inferior reasoning capabilities. The paper also explores parameter efficiency in ToolLLaMA, showing that while improved efficiency is achieved with LoRa tuning, there is a trade-off in performance. Lastly, the paper aims to understand how SOTA LLMs acquire tool usability, as open-source LLMs still lag behind in this aspect. Section: Instruction Tuning and Data Augmentation. We aim to improve the way language learning models, LLMs, understand and respond to human instructions through a process we call instruction tuning. However, manually annotating data for this process can be quite laborious. To address this, we propose a method called self-instruct, which generates high-quality data from state-of-the-art LLMs. This method aligns with the recent trend of curating data for multi-turn dialogues. However, we acknowledge that learning to use tools is inherently more difficult than dialogue due to the wide variety of APIs and the complexity of instructions for using multiple tools. Even the most advanced models, such as GPT-4, often struggle to find a valid solution path, making data collection challenging. Current datasets and methods for tool learning are still in their early stages and are not yet capable of effectively addressing real human needs. To address this, we've designed ToolBench, which is tailored for practical scenarios and improves upon previous methods for constructing tool learning data. Our goal is to enable LLMs to adapt to a variety of tool use scenarios, rather than focusing on a specific type of tool, which we believe is less practical. We also use prompting to help LLMs break down complex tasks into manageable subtasks and generate actionable plans. A method called React aims to better integrate reasoning with action by allowing LLMs to justify their actions and incorporate feedback from their environment. However, these studies lack a mechanism for retracting decisions, which can lead to a chain of errors if an initial mistake is made. A recent approach called reflection attempts to address this by encouraging LLMs to reflect on past failures and adjust their decision-making accordingly. We've expanded on this idea with our method, DFSDT, which allows LLMs to evaluate different reasoning paths and choose the most promising one. While our approach shares similarities with the recent tree of thought, TOT, reasoning method, our DFSDT is designed to tackle general decision-making problems where the decision space is infinite. This is in contrast to TOT, which is designed for simpler tasks that can be solved with a brute force search, such as the game of 24 and crosswords. Our method is designed for a wide range of decision-making tasks, while TOT is specifically tailored for a selected set of tasks. Section Summary. Instruction tuning and data augmentation are important for enhancing language models' understanding of human instructions and generating appropriate responses. Existing methods for tool learning data construction are limited, making it difficult to collect data for training models to effectively address real human needs. Prompting language models for decision-making is crucial, and while previous approaches have made progress, they lack mechanisms for decision retraction. Our method, DFSDT, extends reflection to allow language models to assess different reasoning paths and select the most promising one, addressing general decision-making problems with infinite decision spaces.